Hello everyone, good morning. So after a gap, I am continuing with the lectures in classical mechanics. So today I will discuss Hamiltonian dynamics. In my last few lectures, I discussed about Lagrangian dynamics, and in the last lecture I think we discussed about cyclic coordinates and the physical advantage. Now we will move on to Hamiltonian dynamics. As we know, Lagrangian is a function of generalized coordinate, generalized velocity, and sometimes it may have explicit dependence on time. And this J indicates that if you have a system of n degrees of freedom, then you may have n generalized coordinates and n generalized velocities. So Lagrangian depends on q1, q2, etc. qn, q1 dot, q2 dot, etc. qn dot, and sometimes it may have dependence on time. So this is a Lagrangian. And the Lagrange's equation, it is a set of n second order ordinary differential equations. This J can take values 1, 2, etc. up to n. So you will get the first equation as dou L by dou Q1 minus d by dt of dou L by dou Q1 dot equal to 0. Similarly, dou L by dou Q2 minus d by dt of dou L by dou Q2 dot equal to 0. You can continue up to dou L by dou Qn minus d by dt of dou L by dou Qn dot equal to 0. Even though it appears some partial derivatives there, the final equation will be an ordinary differential equation, and it will be a second order ordinary differential equation due to this time derivative d by dt, and here you have a qj dot, it is nothing but dqj by dt. So there will be ultimately two total time derivatives, so it will be a second order ODE. So this is the Lagrangian dynamics. Now solving a second order ordinary differential equation is difficult when you compare it with solving a first order ordinary differential equation. So it is always beneficial if you can split this second order ordinary differential equation into two first order ordinary differential equation. Okay, this is a simple mathematical trick. You can convert a second order ODE into two first order ODE. That is the only thing we are doing in Hamiltonian dynamics. There is nothing new in this. Concept wise there is nothing new, but it is a mathematical method. Here you will define a quantity which is known as Hamiltonian. It is indicated as H. It is a function of Qj, Pj and time. Qj's are generalized coordinates. J can take values 1 to n. So q1, q2, q3, etc. qn. This Pj is known as generalized momentum or canonical momentum or conjugate momentum corresponding to the coordinate qj. And the definition is Pj equal to dou L by dou qj dot. Pj equal to dou L by dou qj dot. So if you replace the dependence of qj dot with Pj, then Lagrangian becomes Hamiltonian. Okay, Lagrangian is a function of generalized coordinates, generalized velocities and time, while Hamiltonian is a function of generalized coordinates, generalized momentum and time. And using this Hamiltonian, we can show that this second order ODE will convert to two first order ODE. One is qj dot equal to dou h by dou pj and pj dot equal to minus dou h by dou qj. These two are actually first order ordinary differential equation. Due to the total time derivatives appeared here, qj dot is actually dqj by dt, pj dot is dpj by dt. So both these are first order ODE. So if j can take values 1 to n, then you will have a total of 2n first order ordinary differential equation instead of n second order ordinary differential equation. So that is the procedure. Okay, if you can find the Hamiltonian function, then the Hamilton's equations will be first order ordinary differential equations, and the solving first order differential equation will be easier compared to solving second order differential equations. Okay, so this is all about Lagrangian and Hamiltonian. Now I will explain with one example. You consider the harmonic oscillator equation m d square x by dt square plus kx equal to 0. This is a second order ordinary differential equation. Now the procedure is, let's define p, some variable p is equal to m into dx by dt. Okay, p is equal to m dx by dt. Then substituting this in equation 1, equation 1 becomes dp by dt plus kx equal to 0, because p is m into dx by dt. If you substitute that here, you will get this equation. So using the substitution p equal to m dx by dt, this first equation becomes a first order ordinary differential equation, that is dp by dt plus kx equal to 0. And this definition 2, you can write it as m dx by dt equal to p. So these are two first order ordinary differential equation, and these two are equivalent to this second order ordinary differential equation. Okay, this is a simple mathematical way to split a second order ODE into two first order ODE. This is what exactly we are doing in Hamiltonian dynamics. For example, in the case of harmonic oscillator, Hamiltonian is p square by 2m plus half kx square. And the Hamilton's equation, it is x dot equal to dou h by dou p, it is p by m. P dot equal to minus dou h by dou x, it is minus kx. These are Hamilton's equation. Okay, and the Lagrangian is half mx dot square minus half kx square, and Lagrange's equation, that is d by dt of dou L by dou x dot, that will give you mx double dot plus kx equal to 0. So this is exactly this equation, equation 1. Mx double dot is nothing but d square x by dt square plus kx equal to 0. And this x dot equal to p by m, that is this equation, p equal to m into dx by dt, and p dot equal to minus kx is this equation. Okay, so in the case of harmonic oscillator, this Lagrange's equation is equivalent to these two Hamilton's equation. So in all problems, we can use this technique in order to reduce a second order ordinary differential equation into two first order ordinary differential equation. That is the main point in Hamiltonian dynamics. Okay, now I will explain how we can find Hamiltonian from Lagrangian. And that is again a mathematical technique, and that is known as Legendre transformation. Legendre transformation. So I will explain what is mean by Legendre transformation first. Then we will move on to how can we transform Lagrangian into Hamiltonian. Suppose you have a function which is a function of single variable and the independent variable is x. So f is a function of x, and you want to find a function g which is a function of another variable y, and this y has a dependence on x and f, and that is nothing but y is dou f by dou x. Here actually no need to write a partial derivative, you can write total derivative df by dx, because f depends only on one variable. So if you have a transformation like this, f of x to g of y, such that y is df by dx, then the rule is g of y equal to f of x minus xy. This xy, the product of variables that are interchanged. Okay, here you changed the variable x to y, so you have to subtract the product of that variables xy from the original function, okay, to get the new function g of y. G of y equal to f of x minus xy. I will give you an example. Say f of x is equal to x square plus x plus 1. Then y equal to df by dx becomes 2x plus 1, 2x plus 1, and x is equal to y minus 1 by 2. Okay. g of y, by definition g of y equal to f of x minus xy. F of x is x square plus x plus 1 minus xy. X into y is 2x plus 1. So substitute that here. Then you will get it as minus x square plus 1. Minus x square plus 1. Substitute back for x because g is a function of y. So you have to express it in terms of y. That is very important. So minus x is nothing but y minus 1 by 2. So x square is y minus 1 the whole square by 4 plus 1. So Legendre transformation of x square plus x plus 1 is minus y minus 1 the whole square divided by 4 plus 1. This is Legendre transformation. This is a function of x, this is a function of y, and y is nothing but df by dx. Such a transformation is known as Legendre transformation. Now, for Legendre transformation to be valid, there is a condition. F of x should be a convex function. What is the meaning of convex function? Convex function means a function which have positive curvature. Okay, convex function means a function which have positive curvature. If a function have negative curvature, it is known as concave function. And if the curvature is positive, it is known as convex function. And for a function f of x, curvature is defined as the second derivative. F double prime x gives you the curvature. I will explain using these graphs. You consider a graph for f of x equal to constant c. Okay, in this axis you have variable x, the vertical axis you have f of x, and f of x equal to a constant c. That will be something like this, a straight line parallel to x-axis. Then if you take the first derivative, f prime x versus x, the second graph is f prime x versus x. F of x is constant, f prime x is nothing but the slope of this graph. Slope of this graph is 0, so f prime x is equal to 0 throughout. And the second derivative, f double prime x, the third graph is second derivative versus x. F prime x is 0, the slope of this graph will give you second derivative. Okay, f of x, the slope will give you f prime x, the slope of f prime x will give you f double prime x, and that is again 0. So if f double prime x is equal to 0, the curvature is 0. No curvature for this line, it is a straight line. Again, if you consider a straight line which is inclined to x-axis, something like f of x equal to x, then the first derivative is f prime x. It has a constant positive slope because this line is slanting towards right. If a line is slanting towards right, it will have a positive slope, and it is a straight line, so the slope is constant throughout, so it is a positive constant slope, the first derivative. If you take one more derivative, then the derivative of this red line, that will give you 0 because the slope is 0 throughout. So f double prime x is 0. Again, this line has no curvature and the second derivative is 0. If you consider a graph like this, f of x is equal to x square, it is a parabola like this, opened up. If you take the derivative, this parabola is actually right, it is slanting towards right, so the slope is positive, and its magnitude, here the slope is almost 0 and it is going increasing. So slope is increasing as you increase x. So it is, since it is quadratic, the first derivative is linear, so it is a straight line. Slope is positive and it is increasing. While you take the second derivative of this line, this has a constant positive slope. So second derivative is positive. F double prime x is 2, which is greater than 0. So second derivative positive implies the original curve has a positive curvature. Positive curvature means it is opened up. It is opened up. Okay. So curvature is positive if f double prime x is positive. I will give you another example. You consider a curve like this. It will have the form like minus x minus c the whole square plus c square. If you put x equal to 0, you will get 0, and for other values of x, you will get a curve like this. And in this part, if you take the derivative, then it will be minus 2 into x minus c, that is with a positive y-intercept 2c and negative slope minus 2. It is a straight line like this. If you take one more derivative, it is a straight line slanting towards left, so the slope will be negative and it is a constant value. So f double prime x is minus 2, which is less than 0. So this curve is opened down, so it is a concave one. The curvature is concave, so second derivative is negative. So for any curve, you can find whether its curvature is positive or negative or curvature is 0 by evaluating the second derivative. Okay. So the condition for validity of Legendre transformation is simply f double prime x is greater than 0. That is, f of x should be convex. F of x should have positive curvature. If in a single graph, something like this, you can see that this portion has negative curvature, it is opened down, and this portion, it is having a positive curvature, it is opened up, and this portion has a negative curvature, this portion has a positive curvature, like that. Okay, if a curve is opened up, it will have a positive curvature. If a curve is opened down, it will have a negative curvature. Okay, so in our previous example, f of x equal to x square plus x plus 1. The first derivative is 2x plus 1, second derivative is 2, which is greater than 0. So that function is convex function, that is, it has having positive curvature. Now if you consider something like f of x equal to e raised to x, its first derivative is again e raised to x, second derivative is again e raised to x, and e raised to x is always positive. That means e raised to x is a function which is having a positive curvature. This red curve represents e raised to x. This is a function having positive curvature throughout. If you consider a function like sin x, you can have regions of positive curvature as well as regions of negative curvature. And it is its curvature is positive for pi to 2 pi. In the region pi to 2 pi, it is opened up, pi to 2 pi. Then from the region 3 pi to 4 pi, it will again opened up. But in the region 0 to pi, it is concave. So the same function, in some region it can be concave and in other regions it can be convex. Okay. So the curvature of a function can be positive or negative or 0. And if it is positive, it is known as convex. If it is negative, it is known as concave. And for Legendre transformation to be valid, the curvature should be positive. Now, consider this transformation f of xy to g of uv. Here both the variables x changed to u, y changed to v. But this transformation, along with this condition, u have dependence on f and x. That is, u is partial derivative of f with respect to x. Here you have to write partial derivatives because f is a function of two variables. Similarly, v is dou f by dou y. So if these two conditions are satisfied, then g of uv, you can write it as f of xy minus the product of variables that gets exchanged, x to u, y to v. So you have to subtract u into x and v into y. Okay, so g is equal to f minus ux minus vy. This is Legendre transformation of a function f of xy. And here, what is the condition for validity of this transformation? If you consider the second derivative, here you can have different second derivatives. For example, you can take the second derivative of f with respect to x only, that is dou square f by dou x square, or you can have dou square f by dou y square, or you can have dou square f by dou x dou y, or you can have dou square f by dou y dou x. So here, in order to check the validity condition, you have to take the determinant of this matrix. Okay, it is not enough to check whether any of this second derivative is positive or not. You have to check the determinant of this matrix, and this matrix is known as Hertzian matrix. and it is dou square f by dou x square, dou square f by dou x dou y, dou square f by dou y dou x, dou square f by dou y square. If this determinant is greater than 0, that Legendre transformation is valid. Now you can extend this Legendre transformation into functions having more variables, and the condition will be simply the determinant greater than 0. Okay, so this is a Legendre transformation. Now I will give you an interesting example of Legendre transformation. It is not in classical mechanics, but in thermodynamics. In thermodynamics, we have 4 variables basically: pressure, volume, temperature, and entropy. And 4 thermodynamic potentials are there: internal energy, enthalpy, Helmholtz free energy, Gibbs free energy. So 4 variables and 4 potentials. And the interesting fact is, this all potentials have a dimension of energy, and among the variables, PV has dimension of energy and TS have dimension of energy. So PV always have dimension of energy, TS have dimension of energy. Now the first law of thermodynamics is heat given to a system is used for 2 things. One is to increase the internal energy, the U is internal energy, and for doing external work, dW. And from the second law of thermodynamics, dQ is TdS. Also we know that the mechanical work done is given by PdV. If a pressure P can change the volume by dV, then mechanical work done is PdV. So substituting these two here, we will get TdS equal to du plus PdV. That is du equal to TdS minus PdV. du, a differential change of internal energy, depends on a differential change of entropy and a differential change of volume. So we can say that this internal energy is a function of S and V. Internal energy is a function of S and V. Okay, so du is du has terms like ds and dv. That means u is a function of S and V. du is TdS minus PdV. In the same manner, you can write expressions for dH, dF, dg, all the thermodynamic potentials. Okay, in order to write that equations, I will draw a diagram. It is something like this. And in this diagram, in the left top, you have G, then P pressure, then H enthalpy, then entropy S, U internal energy, V volume, F Helmholtz free energy, T temperature. So consider a diagram like this. And in this diagram, if you are taking a particular thermodynamic potential, say H, then here there are 2 arms, one to the right and one to the top. If you consider U, one to the top and one to the left. If you consider F, one to the bottom, one to the left. For G, there is one to the bottom, one to the right. So there are terms to right, left, top, bottom. If you have a term to the right or top, it should be taken as positive. And if you have a term to the bottom or left, you should take it as negative. I will explain. You consider U, then there are 2 neighbors for U. One is volume V and the other one is entropy S. That indicates U is a function of S and V. U is a function of S and V. And if you consider enthalpy H, there are 2 neighbors for enthalpy H. That is S and P. So H is a function of S and P. And for Helmholtz free energy F, there are 2 neighbors T and V. It's a function of T and V. And for Gibbs free energy, it has 2 neighbors T and P. So it's a function of Pt. Now if you take du, it will have terms ds and dv. So you can initially write du is equal to something into ds, something into dv. Okay, you can write like this because u has dependence on s and v. So a differential of u will have terms ds and dv. Du has dimension of energy. So right hand side the terms should have dimension of energy. So the only term which will give you dimension of energy along with the entropy is temperature. So you have to write it as T, TdS. Along with the V, the only term which gives you the dimension of energy is P. Now the remaining thing is to put a sign, and here you can see that S is upward, up means positive, V is left, left means negative. In a graph, up and right are positive, left and bottom are negative. So you have to put a negative sign for V. So TdS minus PdV. This is exactly what the first law of thermodynamics. So you can simply write that equation using this diagram. du equal to TdS minus PdV. I think it is clear. Now, in a similar manner, you can write dH. So, first you have to write it as dH. So, H has dependence only on S and P. So, you have to write ds dP. And along with the entropy, you should write T. Along with the pressure, you should write V in order to get the dimension of energy. Now, the remaining thing is to put a signature. What is the sign? Not signature, sign. Okay. What is the sign of S? It is towards right, it is positive. What is the sign of P? It is towards top, it is positive. So both are positive. The equation is VdP plus TdS. VdP plus TdS. Okay. You can see that equations here. In a similar manner, dF, the dependence is dV and dt, and both are negative because one is down, one is left. So minus S dt minus PdV. dg, you have dp and dt. So vdp and sdt, but sdt is negative. So these are the four differential changes of potentials: du, dh, df, dg. Okay. Now I am saying this as an example of Legendre transformation. So what is the Legendre transformation here? Suppose given internal energy, which is a function of S and V, you want to find enthalpy H, which is a function of S and P. So you can see the brackets. S is remained as the same, but V changed to P. V changed to P. So you can write H is equal to U minus PV, right? U minus PV. By the definition of Legendre transformation that we already discussed, it is something like the new function is old function minus the product of variables that interchanged. Here the variables that interchanged is V and P. So by the definition, we are going to write H is equal to U minus PV. But this will give you a wrong answer. Why? Because when you write like this, H is equal to U minus PV, dH becomes du, this green one, du minus PdV minus VdP. If you take a differential change of this equation, dH is equal to du minus PdV minus VdP. But du, we already know, TdS minus PdV, TdS minus PdV. Again, this minus PdV minus VdP. So this volume dependence will not cancel. It will get added up. So this H will have dependence on S, V and P. But your enthalpy should only have dependence on S and P. So this volume dependence should cancel. In order to cancel this negative term, this term should be positive. That is why the correct expression will be H is equal to U plus PV. If it is U plus PV, du is dH is du plus PdV plus VdP. du is TdS minus PdV. Then this PdV plus VdP. These terms will cancel and H will be a function of S and P. So this sign you have to put according to the situation. The dependence of V should cancel and this H dH contains only ds and dP. Okay. So in order to get that, you have to put the sign correctly. So the correct transformation is H is equal to U plus PV. H is equal to U plus PV. I think it is clear. Now, the remaining equations. F is a function of the relation between f and u. Okay, I will write relation between f and u. Given u is a function of s and v, find f is a function of t and v. Okay, f is a function of t and v. So what is the Legendre transformation? Here f is equal to u. This v is the same. The changing variable is t and s. You have to write u and then ts. Then what is the sign of this ts? Plus ts or minus ts? In order to write that, you go to the arm of u. You go to the arm of u. Okay. Here this is the arm of u. Here s is given as positive. Okay, s is on the top, so it is positive. So in order to cancel this s, you have to put a negative sign here. So that sign will be negative, because when you write df, there will be du minus tds minus s dt. In du, you have tds as positive. Then this minus tds will cancel with that. Minus tds will cancel with that. So in the original function, if it is like a positive quantity, then you have to put a negative sign here. In u, internal energy, s is positive. So you have to put a negative sign here. Then only your TDS will cancel and eventually f will become a function of TDS minus, this is not VDP, it is PD. It will become a function of V and T. Okay. Now, given u as a function of SV, find g as a function of t and p. Then you can see that you can write g is equal to u. Then the variables exchanged are t and s, p and v. You have to write it like this, not tp or sv. You have to write always ts and pv, because these have dimension of energy. Now the remaining thing is to put a sign. In u, the sign of s is positive. So you have to write a negative sign here for the term which contains s. Similarly, in u, v is negative. So in this expression, you have to put a plus sign. So g is u minus ts plus pv. G is u minus ts plus pv. Okay, so you can write any expression. Given g, which is a function of Tp, find f. That is the relation between Helmholtz free energy and the Gibbs free energy. So here T is the same. So in order to write f, you have to write g. T is the same. The variable that exchanged is Pv, P and V. Now you have to go to g. In g, this P is like positive. Positive is towards right. So you have to write negative sign here. So f is equal to g minus Pv. So altogether you can write 6 expressions. H is equal to u plus Pv, f is equal to u minus Ts, g is equal to u minus Ts plus Pv, f is equal to h minus Ts minus Pv, g is equal to h minus Ts, g is equal to f plus Pv. These are the 6 expressions. Okay, by simply inverting this, you can find other ones also. These are the 6 independent equations connecting the 4 thermodynamic potentials. Okay, so you can easily write this using this diagram. And here the Legendre transformation. Here comes the Legendre transformations. Okay. Now, in order to study this G, P, H, S letters, where to write that or how to remember that, you can use this wordings. Good physicists have studied under very fine teachers. Okay. And one more thing, you have to be careful. in starting writing with the left to top. Okay, you have to start writing left to top, otherwise all these things will be incorrect. Okay, so this is the way to remember this. Good physicists have studied under very fine teachers. Now, if you have these expressions du equal to TdS minus T PdV, you can derive Maxwell's equations because you can derive the partial derivatives dou u by dou s at a constant volume. Dou u by dou s at a constant volume, that will be simply T. Dou u by dou v at constant entropy, that will be minus P, and like that. So from 4 thermodynamic potentials, you can get 8 partial derivatives like this. From that you can obtain Maxwell's equations and all. Okay, so the entire thermodynamic equations you can write using this diagram. Okay, now coming to classical mechanics, what is the Legendre transformation? Here Lagrangian is qj dot t. It is a function of generalized coordinate, generalized momentum and time. And Hamiltonian is a function of generalized coordinate, generalized momentum and time. So you can see that this qj dots exchanged with pj. Actually j can take values 1 to n. So there are n qj dots here and n pjs. So q1 dot exchanged with p1, q2 dot exchanged with p2, q3 dot exchanged with p3. And all these variables have connections. P1 is dou L by dou Q1 dot, P2 is dou L by dou Q dot, dou Q2 dot, P3 is dou L by dou Q3 dot, and so on. So it already satisfies the conditions for Legendre transformation. F of xy to g of uv. The Legendre transformation is possible if u is dou f by dou x, v is dou f by dou y. In a similar manner, you have here P is dou L by dou Q1 dot P1, P2 is dou L by dou Q2 dot, and so on. Therefore, you can write Hamiltonian is equal to Lagrangian minus P1 Q1 dot minus P2 Q2 dot minus P3 Q3 dot, like that up to Pn Qn dot. Okay, so in the first look, you have the relation Hamiltonian H is equal to Lagrangian L minus sigma j equal to 1 to n pj qj dot. But we will see that in most of the cases Hamiltonian turns out to be the total energy of system. Okay, and we will see that in the coming sections. Hamiltonian turns out to be the total energy of the dynamical system in most of the cases. There are exceptions, but in most of the cases Hamiltonian turns out to be total energy of the system. And in order to make the sign of energy intact, we should write this in the other way. That is, H is equal to sigma pj qj dot minus L. Otherwise, the sign of energy will be different. Okay, that you will understand when I do some examples. Okay, so the correct way to write this is sigma pj qj dot minus L. The concepts of Legendre transformation, it won't change if you take like this also. Okay, H is equal to sigma j equal to 1 to n pj qj dot minus L. This is the way to obtain Hamiltonian given the Lagrangian. Now, I will give you an example. If you have only 1 degree of freedom, H is equal to PQ dot minus L. PQ dot minus L. Lagrangian is equal to half m x dot square minus half k x square. This is the Lagrangian of harmonic oscillator. The steps to obtain Hamiltonian. The first one is the basic equation. H is equal to the variable that changed is you need a function which is a function of x, p and t, right? Lagrangian is a function of x dot and t. There is no explicit dependence on time, so Hamiltonian will be independent of time. So you need L L is a function of x and x dot, you have to convert it to h, which is a function of x and p. So the variables exchanged is x dot to p. So you have to write h is equal to px dot minus l. Px dot minus l. P is dou L by dou x dot, that is equal to mx dot. So the third step is x dot is equal to p by m. From this second step, x dot equal to p by m. Now h is equal to p is mx dot into x dot minus l, half mx dot square plus half kx square. So this is mx dot square minus half mx dot square, that becomes half mx dot square plus half kx square. Then the final step is, this is not a Hamiltonian because this is expressed as a function of x and x dot. Hamiltonian should always contain the generalized momentum. So you have to replace x dot in terms of momentum. So x dot is p by m from 3. So that becomes p square by 2m plus half kx square. This is Hamiltonian for one-dimensional harmonic oscillator. Okay. Now you consider the case of planetary motion. What is Lagrangian for planetary motion? It is half m r dot square plus r square theta dot square minus gmm by r. Not minus, it is plus. Because potential energy is minus gmm by r. L is T minus V. Now, the first step is h is equal to, here you have two coordinates. So you will have two momenta, pr r dot p theta theta dot minus l. Okay. So you have to sum over all the generalized coordinates. So here you have two coordinates r and theta. So in the conversion equation you have pr r dot and p theta theta dot. The second step is pr. What is pr? pr is dou L by dou r dot. It is m r dot. Similarly p theta, it is dou L by dou theta dot. It is m r square theta dot. In the third step, you can write r dot, the inverse relations, pr by m, and theta dot, that is p theta by m r square. In the fourth step, you can substitute back the value of pr and p theta, the first starting equation. Step 1, it is m r dot into r dot plus m r square theta dot into theta dot minus l, half m r dot square plus r square theta dot square minus gmm by r. So this becomes h is equal to m r dot square minus half m r dot square, that becomes half m r dot square, m r square theta dot square minus half m r square theta dot square. So it is half m r square theta dot square minus gmm by r. And the final step, you have to convert all the velocities, generalized velocities, into generalized momentum using step 3. So h is equal to pr square by 2m plus p theta square by 2m r square minus gmm by r. Simply put r dot as pr by m, theta dot as p theta by m r square. You will get like this. So this is the way to write Hamiltonian from Lagrangian. So for any system, you can follow this procedure to write Hamiltonian. I hope it is clear. Now, I will discuss Hamilton's equations of motion. Hamilton's equations of motion. So you have h, it is a function of qj, pj and t. Okay. Then what is dh by dt? It is dou h by dou qj into qj dot plus dou h by dou pj into pj dot plus dou h by dou t. Equation number 1. Also we have h is equal to pj qj dot minus L. From here you can write dh by dt as pj into dqj dot by dt plus qj dot into dpj by dt minus dl by dt, right? But L is a function of qj dot and t. So again for the last term you can apply chain rule. Therefore dh by dt becomes pj into dqj dot by dt plus qj dot into dpj by dt minus this becomes dou L by dou qj into qj dot minus dou L by dou qj dot into dqj dot by dt minus dou L by dou t. But from Lagrange's equations of motion, this term dou L by dou qj is d by dt of dou L by dou qj dot. Okay, dou L by dou qj is d by dt of dou L by dou qj dot. Dou L by dou qj dot is pj, generalized momentum, so that becomes pj dot. So whenever you have this dou L by dou qj, replace it with pj dot. Then what is this dou L by dou qj dot? It is pj. So you can cancel this term pj. This is pj dqj dot by dt, and here you have minus pj dqj dot by dt. This will get cancelled. Then you can compare these two equations. The equations for dh by dt. Then you can see that this, comparing the coefficients of qj dot, this is actually dou L by dou qj is pj dot. Pj dot is equal to dou h by dou qj, and comparing these two terms, dpj by dt is pj dot. So coefficient of pj dots becomes qj dot equal to dou h by dou pj, and minus dou L by dou t becomes dou h by dou t. So comparing these two equations 1 and 2, you can write, comparing 1 and 2, from 1 and 2 you can write pj dot is equal to minus dou h by dou qj, qj dot is equal to dou h by dou pj, and dou h by dou t is equal to minus dou L by dou t. Okay, we'll get these three equations comparing 1 and 2. And this set of 2n first order equations, then one partial differential equation. Okay, these 2n first order equations are known as Hamilton's equations. Qj dot is equal to dou h by dou pj, pj dot equal to minus dou h by dou qj. I will give you an example. Again, a harmonic oscillator. H is equal to p square by 2m minus half k x square. So first equation, p dot is equal to minus dou h by dou x, and that becomes kx not h is equal to plus half kx square. P square by 2m plus half kx square is a Hamiltonian. So this becomes minus kx. And x dot is equal to dou h by dou p. It is p by a. P by a. So you have two first order equations. One is dp by dt equal to minus kx. And the second one is dx by dt equal to p by a. These are the two first order ODE. Two first order ordinary differential equations. They are not partial differential equation, they are ordinary differential equation. And we can see that this is equivalent to Hamilton's equation, Lagrange's equation, because you can substitute for p in this equation. P is m into dx by dt. That means d by dt of the first equation, d by dt of p, you can write it as m dx by dt equal to minus kx. So this becomes m into d square x by dt square plus kx equal to 0. This is exactly Lagrange's equation. So two first order equation is equivalent to this second order equation. Or you can split this second order equation into two first order equations by defining such a function h. So this is the procedure of Hamiltonian dynamics. Okay, so this is actually a mathematical procedure in order to split a second order ordinary differential equation into two first order ordinary differential equation. If you have a system of 2 degrees of freedom, you will have two second order ordinary differential equations, Lagrange equations. In the Hamiltonian procedure, you will get 4 first order ordinary differential equation. Okay, I will give you one more example for planetary motion. What is Hamiltonian? H is equal to pr square by 2m plus p theta square by 2m r square, then minus gmm divided by r. Okay, the first equation, pr dot is dou h by dou r with a negative sign, and that becomes minus p theta square by m r cube plus gmm by r square. And p theta dot, it is minus dou h by dou theta. There is no theta, theta is cyclic, so this is 0. Then r dot, it is dou h by dou pr, it is pr by m. Then theta dot, it is dou h by dou p theta, it is p theta by mr square. So these are 4 first order ordinary differential equations. You can show that these are equivalent to 2 second order ordinary differential equation. Okay. So this is all about Hamiltonian and dynamics. So I explained how we can obtain Hamiltonian from Lagrangian. It is through Legendre transformation, and what are Hamilton's equations, and what is the basic idea of writing Hamilton's equation instead of Lagrange's equation. Okay, thank you.